We're going to talk about how to produce hydrogen by using this fusion reactor that is always hovering above us, and how that works. Stormwell will show us. Please applaud him.
Ja, guten Morgen.
Yeah, good morning.
So,
All right.
dann herzlich willkommen. Schön, dass ihr alle wach seid.
Hearty welcome. Thanks. Good that you're all awake.
Ich bin Chemiker.
I'm a chemist.
Organische Chemie
I have worked with organic chemistry, with biochemistry, and lately with physical and electrochemistry.
Abschlussarbeit am
I wrote a master's thesis at the Helmholtz-Zentrum in Berlin-Wannsee,
Da ging's
and there I dealt with this subject, how to find materials to produce,
Probleme der Zukunft zu lösen.
to solve the energy problems of the future.
Also kurzer Abriss.
So short agenda.
Eigentlich so pro Jahr.
How many agenda do we need per year?
Ich gehe durch ein paar Grundlagen durch.
I'm going to go over some basics. I'm not going to dive deep. Some chemistry and physics from school will be useful. Some of you may remember the basics. Then we'll look at
Zellen an, diese
the well-known silicon photovoltaic cells that are spread over this camp. Then you need to store the energy somehow. I'm going to talk about that shortly.
eventuell mit einer
And then how to couple this way with a new class of materials.
So. Hoppla, leck. Nein. So. Das sind zwei. So. Das sind zwei Diagramme.
These are two diagrams from
Ackertech.
Ackertech.
Eine
It is a
Beratungsgremium
council
Akademie und Technik.
group for academia and technology, Ackertech. That is this pie chart on the left.
Bisher weltweit nur läppische 2%
We have only 2% solar energy,
Energien, aber immer noch
some part of renewable energy, but most of it's still from fossil fuels.
Seite
And on the right side, we see
Diagramm aus
a diagram from the BP annual reports. BP, you know them,
Tankstelle quasi.
the refueling station, the oil producer.
Eine Statistik
They
über den Energieverbrauch hinaus.
write a report on energy consumption every year,
Diesen Spike nach unten.
and you see this spike downwards pretty well 2008, 2009, when the world financial crisis was, and the change went up back again. And now we have an increase in energy consumption of 3% per year, which is a 3-year high. And on the right, we see that the carbon dioxide emissions have also increased. So this climate change thing is everywhere. Everybody's talking about it, and it's time that even more people talk about it. Here's the change over the years, consumption of primary energy. The composition is on the top coal, then in orange the renewable energies, then we have hydroelectricity. The bright orange is nuclear energy, then gas, and in green, oil.
Die Berechnung ist in Megatonnen.
Calculation is in megatons oil equivalent, MTOE.
Die übliche.
That is the usual unit,
Das sind
and these are 166 petawatt hours.
Peta ist das, was
To, as a recall, peta is the one unit after tera, so 1,000 terawatt hours,
pro Jahr gerechnet
or
19 Terawatt
19 terawatt years per year.
kann man im Prinzip kürzen. Das heißt, die Erde
So you could cross it out.
Leistung.
The Earth has a rated power of 19 terawatt.
Zum Glück kommt von der Sonne ein bisschen mehr.
Thankfully, a lot more comes from the energy, from the sun, 179 petawatt, so more or less a factor 10,000 more. That's a graphic from
Quelle NASA.
NASA originally.
Einkommende Strahlung in Gelb.
The incoming radiation in yellow,
Strahlung eben
and the different ways how this radiation is reflected, going back to the universe or staying on the ground. 89 petawatt arrive at the ground. That's more than enough to cover all the demand. Here's a repetition. The more orange you see on the map, the more intense the sun radiation is. That is average over the year. And the black dots are spaces with high radiation, for example, North America, the Great Basin, Nevada Desert, or South America, Atacama Desert, Sahara Desert. And these black dots alone, to cover those with solar panels, would cover the whole energy demand of the world. What is actually reaching us? That's the spectral intensity of sunlight. You remember from school this theory with the black body radiation? That is the yellow curve, and the orange curve is the actually measured radiation outside of the atmosphere. Inside the atmosphere, it's a little bit different. That is the lower curve. You see the rainbow. It's the visible spectrum. And these notches that you can see are actually filtered by water gas in the atmosphere. Water has several absorption bands. On the right side of the graphic, they absorb radiation. That has already been considered in the diagram we just saw before, which also means that the more arid your region is, the less clouds you have, the hotter it will be in the oceans, on the land, and this whole story will run even faster. To standardize all of this, the atmospheric mass model has been developed. We have different details, different level of details. So the first approximation is the Earth. You put a plate on the Earth. You see where does it go back in the atmosphere in a right angle, and the angle between the sun and this reflection is the zenith angle, and then the atmosphere will be passed only once. If you go a bit more to the north or to the south, then even at 12 o'clock at summer solstice, the sun will enter in an angle. That is the AM 1.5. That's the usual radiation force in Europe and Northern America. And because that's the industrial countries, that has been used as a standard for measurements. A bit more to the north, that would be 60 degrees. Scandinavia, for example, that's AM2. That means that the equivalent of 2 atmosphere thicknesses are being traversed by the radiation. And if you see the sun just above the horizon at 90 degrees, in the more detailed models, that is in 38-fold atmosphere penetration. And of course, in space, that is AM0 because there's no atmosphere at all. So you cannot wait until summer solstice to make your measurements when there's absolutely no clouds. So that means in the lab, you need a sun simulator. That is the device I made my measurements with. You see on the left side the control PC. That's where all the electronics is put in. In the middle is the measurement cell. And on the right, this black L is the light source. Here, let's see it in detail. The white thing is the electrochemical cell. The wires go to the measurement electronics. And on the right, we have an aperture in order to go from dark to clear quickly. And on the right, we have a xenon light that you also have in cars. These super clear, bright, bluish lights are xenon lights. Why do we take them? Well, we need to model the sun spectrum pretty efficiently. If you take incandescent lamps, then you reach 3000, 3500 Kelvin. You know, the light temperature, that is exactly that data. And that orange thing is the sun spectrum. And there you see that the blue parts are just not well represented. And therefore, you need that bluish light. And it is modulated with filters in order to reach this equivalent of the intensity in the cell.
About solar cells, we've all seen them before. You start off with sand, arrive at silicon, and this is split into very flat wafers. And you reach these glittering polycrystalline solar cells. It's a monocrystal, like in the chip industry. But in solar cells, you luckily don't need this high purity like you need on chips. In industry, you usually need about 99.999 degrees of purity. In solar industry, 99.5 are enough. So you can work with very simple processes. So how does the current come out of this? On the left-hand side, you see a model, a band model of a silicon semiconductor in the solar cell. The bluish part is the one irradiated by sun, and the red one is the actual material, which you don't see, and in between the electrical current runs. In silicon solar cells, this is 0.6 to 0.7 volts, and the irradiation intensity determines how much current you get out of the solar cell. So if there's a cloud above, it gets darker, and of course, eventually the current and voltage drop down. On the right-hand side, we see what this cell actually absorbs. The dark one is the sun spectrum that comes into the cell. The yellowish curve is the actually used part of the spectrum. In between, you see the band gap at a temperature of 300 Kelvin, which corresponds to the base state of the valence band, going up to the state of the conducting band, and the gap in between is the actual band gap, which you can deduct as a voltage. So the energy is calculated by H times nu, which is the Planck quantum times the irradiation frequency, which is also corresponding to the color of the incoming light. So here, the orange region is the visible light up till infrared spectrum, and then there's a sharp decrease, which is due to the energy of the incoming photons not being sufficient anymore to actually bridge the gap into the conduction band. So this light simply isn't absorbed. This is going to be interesting later in the talk, because this is actually the upper limit regarding efficiency that we can get out of our solar cells, because otherwise the material simply can't catch the photons anymore. So here we have the Bohr atom model, which explains the atom as divided into the core and the shell. So here's an excitation from a second to the third shell, sending out a quantum of light. And this is exactly what we want regarding solar cells. So there's a photon coming in, and there's an energy excitation sending out, generating a voltage difference, which is what we can use in our solar cells. So in a simple band model, in this case magnesia, die Elektronen teilen, die sie zusammen. See that all atoms in one compound share the electrons, the so-called covalent binding, which forms the valence band. And the conduction band is only slightly above this valence band. So with only a little push in energy to the electrons, which they can already assume at room temperature, the electrons can freely move and electronic conductivity is established. However, we choose silicon, which is a semiconductor. In a metal, again, the valence and conduction bands are very close to each other, and the band gap is sufficient. However, in a non-conductor, the conduction band is too far away, so no light and no electrical energy is sufficient to get the electrons into the conduction band. They're stuck with their atom cores, and the material is non-conducting. And the average of these two is the semiconductor, where the band gap is in the region below approximately 4 electron volts, which roughly corresponds to ultraviolet light, and a bit lower corresponding to a yellowish shade. So silicon has a band gap of about 1.2 electron volts, which corresponds to the infrared spectrum of light.
Diese Energie wird ausgedrückt Elektronenvolt, also
This energy is usually expressed in electron volts, which is the elementary charge times the voltage that was obtained by this charge. Up till now, everybody should have heard about this concept. Photovoltaics is known. However, what happens if we get a semiconductor into direct contact with water?
können, ist diese Elektronen, die eben
So photoelectrochemical cells can
Stromkreis außen rumzuleiten, sondern direkt
actually
Wasser in den Kontakt
conduct
und eben
electrons directly into water, so not via an outer circuit, but rather directly into water, splitting the water into hydrogen and oxygen, and by that omitting an outer circuit, which would, of course, cause losses in efficiency.
das ist das Redoxpotential von Wasser.
So the 1.23 electron volts we see is the redox potential of water, which is the minimum potential that has to be surmounted in order to start this process.
Und
Those red arrows are the so-called overpotentials.
idealerweise Wasser sofort
So
eben
the band gap we ideally need to split water into hydrogen and oxygen would be approximately higher than 1.8 electron volts, considering the overpotentials as well.
tatsächlich zeigen können, dass das direkt geht.
And we saw so far that we obtained no material that was actually able to perform this right away. So we had to introduce some tricks.
Photoelektrochemische Zelle, die aus
This is a schematic of a photoelectrochemical cell
das Licht kommt von links.
comprising two half cells. So the light enters the blue layer on the right-hand side. These are very thin layers in the region of 10 to 20 nanometers
100 Nanometern.
in the minimal case, or up to 100 nanometers in a thicker case. But then we have stability issues.
Hier ist es eine Membran oder eben den Elektrolyten, wasserbasiert.
And the rays transcend a membrane, which in this case is water-based, and arrive on the other side on the red photocathode.
Den Prozess
And with the light that still reaches the red side, can start the process of splitting the water.
der Energie
So the electrodes kind of share the work, and only the one electrode has to surmount the work
sieht man das.
to provide the electrons for these processes.
Dann werden dann über einen Leiter außen rumgeleitet und
And the electrons are conducted via an outer conductor, coming back to the photoanode.
ein anderer Ansatz ist jetzt, wir hatten vorhin gesagt, diese Photovoltaikzelle, Siliziumzelle,
I'm sorry, they come back to the photocathode via this outer circuit.
was ist, aber wir haben auch gesagt, wir brauchen höhere Energie, also
So, but then we also said we need higher energies than 1.2 electron volt.
höhere Bandlücken in dem Material hat, wird
If we have higher energies and a larger band gap in the material,
absorbiert, alles
Then-
dann geht verloren.
only higher energy
Was ist jetzt?
radiation is absorbed. Everything below it gets lost. So it's only, for example, ultraviolet or green light.
Und dann sieht das
So what do we do with the remaining radiation? We just send it into the next cell.
Vollspektrumlicht
So from the left-hand side, the full spectrum light
dieses
would reach
auf das gelbe photokatalytische
the
Material.
yellowish photocatalytic material,
Die erste Teil der Reaktion
then performs the first part of the reaction, and the remaining irradiation reaches
durchkommt, ist
the
eben
material behind the yellowish part, which is maybe then in the reddish-yellow spectrum.
eine ganz normale
And on the back side, it just reaches a normal photovoltaic cell.
Das ist jetzt spiegelverkehrt, aber das heißt, dass das Licht mit der Höhe
On the right-hand side, the image is mirrored, but in general, it shows the same processes.
vieles kann. Alles, was es nicht
So the full spectrum light excites as many electrons as it can, everything else that doesn't manage to do that shines through
landet dann in
to
dem
an end-up silicon material,
und kann da immer noch
reaches the silicon solar cell and does its normal work.
zusammen Tandem wie beim
So
Fahrrad.
it's a kind of tandem solar cell working together as a compound.
Man knabbert sozusagen, man teilt diesen orangenen Bereich in zwei Teile.
So we're actually parting this orange region into two parts.
Wird von der
The higher energy part on the left-hand side
Material absorbiert und der
is absorbed by photochemical material and the rest still remains for the silicon solar cell.
hier ist unten dran geschrieben Fe2O3, es ist tatsächlich simpel Rost. Also
Here, this material on the right-hand side is marked by Fe2O3, which is simply
werden verwendet
rust. It's just corroded iron.
Metalloxide,
We usually use metal oxides because they're very practical, they're stable, they're widely available,
System mit
but
50, 60
the problem is, of course, in the periodic table of elements, there's like 50, 60 metals, and then we're running out of possibilities for materials.
Ich gehe nochmal zurück. Das ist hier unten angeschrieben mit dem Pfeil und
So, what other materials could we use? Below the yellowish part, this one is marked as
Vanadium und Sauerstoff.
bismuth, vanadium, and oxygen.
Durchrechnet, wie viele Kombinationen es gibt, ist man ganz schnell im
And if we calculate how many actual combinations of metal oxides we could have, we end up in the 4-digit region. So we have a lot of experimental grounds on which to try which materials and which combination of elements could be suitable for these processes. Because of course they all have different band gaps, they all absorb different energies and could be more or less suitable for the aim of splitting water.
So, dann eben noch das Thema mit der Speicherung.
Going back to energy storage,
Energiewende, das ist so ein
this is an excerpt from Agora Energiewende or Energy Transition report,
Verbrauch entwickelt.
marking the German-wide energy consumption
Mai.
over 1.5 months.
Eine Kurve ist tatsächlich
So the purple curve in the middle is the most interesting one.
Entschuldigung, nein, die pinke Kurve ist
No, it's actually the pink one,
an Strom.
which is the demand for energy.
Kam man tatsächlich in den Bereich, dass die regenerativen Energien
On the 1st of May, we actually entered the region that regenerative energies would have been able to actually cover the whole demand.
geht auf verschiedene Faktoren zurück, teilweise
That can be put down to different factors.
Strahlung.
So, of course, we had a very high sun irradiation. It was a public holiday in Germany, so with a quite lower energy demand. And for the first time, we found this inversion that could have actually just been able to shut down conventional power plants and use the renewables instead.
Normale Elektrolyse, auch das hat wahrscheinlich jeder mal im Chemieunterricht in der Schule gesehen.
One of the applications would be simple electrolysis. Everyone might probably have seen this in their chemical lessons. So we put in electricity in the water and split it into its components, hydrogen, oxygen, which works quite well in principle. Unfortunately, the most effective electrodes in this context are platinum electrodes.
Von Wasserstoffevolution. Dummerweise packen wir das nicht in solche
So platinum is the material that
Fließens irgendwo in der Bank.
very much is most efficient in splitting water, performing electrolysis.
So Metalle wie Iridium oder
It's also not as rare as metals like iridium, for instance,
die auch teilweise in unserer modernen Elektronik
which, for instance, are also components of our modern electronic devices. These are an order of magnitude rarer.
wenn man jetzt den Prozess in eine Zelle zusammenbaut,
However, if we
drei tatsächlich
Add-
Konzepte zusammenbaut,
all three concepts that I mentioned within one photoactive cell,
verschiedene Halbleiterzellen,
which means generating a stack of 3 different semiconducting materials which absorb different colors, marked by blue, green, and red here in this case,
damit werden die in Reihe geschaltet, die Energie wird
which are then
gepumpt,
conducting in series or setting up a series
eingetaucht. Und dann hat
and immersed in water. Then we actually have a cell
Wasserstoff und Sauerstoff erzeugt.
which can split water into hydrogen and oxygen by only being irradiated by light.
funktioniert das Video bei mir auf dem Bildschirm, aber nicht.
So on my screen, the video doesn't work.
Ich sehe es leider nicht. Es blubbert, hervorragend. Genau das möchte ich zeigen.
There's bubbles. This is actually what I want to show in this video.
Der Kreis auf der linken Seite ist die Seite, wo Wasserstoff.
So the circle on the left-hand side is where hydrogen is developing.
H2O 2:1, die Blasen sind größer.
We know that stoichiometrically the bubbles have to be larger.
Und auf der anderen Seite ist Ruthenium.
So this is covered with platinum, and on the other side, on the right-hand side, we have ruthenium oxide on the electrode, which is also a quite rare metal and one of the only oxides that are actually able to catalyze the oxygen reduction reaction or oxidation reaction in this case in a very good way.
Und Sauerstoff tut sich da ein bisschen schwerer. Das heißt, es
So in general,
Überzeugungsarbeit.
oxygen needs a kind of
Roten Pfeile oben und unten.
conviction
Und die möchte man natürlich auch
to
reduzieren, weil
participate in this reaction, which of course we want to reduce because the overpotential times the applied current is an electrical power output, which we lose in this case in the reaction.
schon mal in der Schule gesehen. Das ist
I guess this everybody has seen in school as well. That's a kind of biological cell, the chlorophyll in the nature.
das erste Chromophor absorbiert.
The same principle. First chromophore absorbs light of a first wavelength. It's excited. Then over this step that you see in the next, it deactivates a little bit. Then on the second photosystem, it is re-excited and gets a harder push. And the energy of the second photosystem is strong enough to push the following reaction and carry out the photosynthesis in the plant.
So, das wäre der grobe.
So that would be the big picture. I hope that you have more questions than before,
Und davon würde ich gerne ein.
and I would like to answer some of those.
So, ihr kennt das schon.
Okay, you know the drill. There's two microphone angels, one on the left, one on the right. Please go see them if you have questions. If you're in the stream, you have lost because there's no signal angel. I'm very sorry. Hi. How is it with efficiencies and wear and tear of the materials that are being used? Yeah, that's a good point. Silicon solar cells, well, the theoretical limit is 32-33% from thermodynamics. In practice, the best cells have a bit more than 20%. The super expensive for military and space applications have 25%. The electrolysis behind, depending on how good and expensive the catalysts are, 70, 80, maybe 90%.
Das sind dann halt in
That means in the sum we have 15-20%.
dieser Stapel.
In this stack cell where we saw the video, there was the efficiency written next to it. 9.5%, that is pretty good. But I mean, these materials deliver efficiencies. We're talking about the solar to hydrogen efficiency, STH.
Meistens
That is usually below 1%, sometimes maybe 1 point or 2 point something percent. There's a lot to do.
und die Stabilität
And the stability, also a good point, is generally
dieser Wasserspaltung auch
in the process the material is being corroded. In general, we bring on passivation layers to enhance the lifetime. So in the lab, we reach lifetimes of a week or something like that. And usually that is already good. But sometimes within minutes they get decomposed. So we need to look at these thousands of combinations of which material works, has good efficiency, and isn't decomposed within minutes.
Eine weitere Frage von dort.
Another question from that side? Hi. I saw in the media that apparently a company has developed a prisma to use the to shift the unusable part of the light spectrum into the usable part. Well, for me that sounds like frequency doubling. There are nonlinear optics.
Laserpointer gesehen.
Who of you has already seen a green laser pointer?
Ungefähr alle im Raum, ja.
More or less everybody.
Das ist tatsächlich
That is actually an infrared laser that is being sent through
Frequenz und dann
this nonlinear optics, which sends out everything that is green, but it only works very selectively for a narrow spectrum. So I don't know if that is actually what you mean, but otherwise convert the color. Yeah, I don't know a process that can do that. And I don't know how efficient that would be. And these green laser pointers have a terrible efficiency from electrical power to light.
Dann machen wir gleich weiter.
Okay, let's move on.
Kleinere und größere Frage. Die kleine
A small question and a big question. Small question is
der Notwendigkeit der Reinheit des Wassers.
how necessarily clean, how clean does the water need to be? I guess that if you take just tap water in large quantities, that after some time the catalysts will be dirty or something like this.
Bevor das Wasser abkochen mit Energie.
You generally don't want to clean the water
Andere Frage.
with a lot of energy, I guess. And the other question,
Uns
can we
überlegen, die
imagine molecules that are specially engineered
Licht aufzunehmen und
to absorb light and split water in hydrogen and oxygen?
so ein Molekül hätte, könnte man vielleicht eine
I mean, if we had that molecule, we could maybe create a DNA strand that we can put into bacteria and then engineer bacteria in order to
im Prinzip
carry out
unsere eigene Form von
that electrolysis or that photosynthesis that splits water.
Ich weiß nicht, ob wir schon so
I
weit
don't know if we're so far in the technology.
Wasserreinheit.
First question regarding water purity. Well, I've only dealt with lab setups, so we have ultra pure water, which is called millipore, has super low conductivity, almost none impurities inside. Because the problem is we're talking about redox chemistry. So if other redox active materials are implied, salt, metals, lead, copper, they are also being reduced and oxidized electrochemically. So in general, you will be dropping copper or lead. You can poison your material with that.
Ja, im Zweifelsfall nimmt
And in doubt, you drop your efficiency. Talking about filters and particles, yeah, you don't want them, so you need to filter your stuff. I can't tell you more detail about that, unfortunately. Regarding the second question,
ja, es gibt so
yeah,
das heißt,
there is such things. That's called Grätzel cell.
tatsächlich schon mal jemand ausgedacht und dafür den Nobel.
Somebody worked on it and received the Nobel Prize.
Organische Farbstoffe.
There was organic colorants
ein
on
Trägermaterial
a
aufgesetzt,
conductive
anzuregen
support,
und die
which was then excited,
Elektronen dann abzuleiten.
and the electrons were led off it.
Ein großer Hit.
There was a big hit for some time. I don't know how that has developed for today. It's a very special.
Man kann sowas prinzipiell auf dem Küchentisch sogar nachbauen.
You can do that at home
Bringen ist relativ einfach. Auch
to make that work. It's pretty simple. I mean, organic colorants, something like
mit Früchtetee machen.
you can do that with fruit tea. Actually,
Hält natürlich nicht lange, weil auch da
doesn't live for a long time. Also here, this the incoming light excites the molecules, but
funktionieren sie nicht mehr.
they wear out and don't work after some time.
Mit einer praktischen Anwendung
So,
sieht das kann ich im Detail.
I don't know how the practical applications look like.
Okay. Noch 10 Minuten.
Okay,
Zeit. Wer
10 minutes left.
noch nicht?
Who wants to ask a question? Maybe from the left mic?
Da, jemand steht.
Ah, there's somebody standing up.
Einmal das Mikrofon an, bitte.
Ja, das ist schon an. Ich habe noch nichts gesagt. Es gibt
There is
diese Kombination.
this combination of solar cells and fuel cells seems only to be working in the lab. There's a lot of talk about, I mean, you can just take solar cells and then an own
Eine Brennstoffzelle dahinter.
solar fuel cell behind it to produce.
Zwischenfrage,
Oh,
Brennstoff.
just a break. You mean fuel cell or electrolysis? I mean electrolysis. Fuel cell comes afterwards to use the hydrogen. Yeah, exactly. That's a whole other chapter. But yeah, my question is,
Ist ja heutzutage schon baubar.
that is
Ähm,
state of the art, isn't it?
viel
is that much more inefficient, or why do you want to go to this direct coupling?
Und wie weit ist das zeitlich noch in der Zukunft?
And how far are we still in the future? That's a very good question. Probably a couple of years ahead.
Solarstrom oder generell regenerative
Solar power or renewable power to electrolysis is being done today.
Das Problem ist,
Problem is, on the one hand,
ich hatte kurz die Folie aufgeworfen.
I put up this slide, sand to silicon to solar cell.
Sieht einfach aus, braucht aber
It seems easy, but needs a lot of energy.
das ist ein sehr gut
It's
erforschter
a very well-researched process, mostly because of the chip industry that had big interest into that.
Herstellung von Solarzellen.
But the production from solar cells needs a lot of energy, and the amortization times are somewhere in the domain of 2, 3, 4, 5 years until the solar cell has compensated, harvested the amount of energy it has cost to being produced.
Im Bereich von Jahrzehnten.
The lifetimes are in the domain of decades, 20, 25, 30 years easily, and that means that after lifetime they still perform 80, 85% of their energy. So one argument would be you can save the
Siliziumdioxid aus Sand.
energy to produce silicon from silicon dioxide.
Die Metalloxide sind
The metal oxides are already energy low materials.
Eisen.
You know that iron is rusting because rust is at a lower energy level than metallic iron.
Das heißt, die Energie
So the idea would be you get the raw materials more easily. Well, silicon is one of the most frequent materials we have in most abundant materials we have in the crust of the earth. But the idea is we want to produce all of that with less energy. And the next point is that electrolysis is only working efficiently and well if you have these expensive, valuable material catalysts, noble material catalysts. So you can lower the system costs instead of building a solar farm and then an electrolyzer, and you have to maintain them. Well, that would be a possibility to save money, but how well that will be in the end, we will see.
Möchte noch jemand?
Does anyone else want to ask a question?
Um vielleicht ein bisschen Zeit zu überbrücken, eine Frage
Or
von,
maybe to bridge some time, I have a question.
forscht jemand aktiv an der Suche nach diesem Material?
Does anyone do active research on these materials?
Arbeitsgruppen, die
So is there any working groups
entweder simulieren oder
that maybe simulate or just try
in der ich war. Zum
Okay.
Beispiel.
these kinds of materials out? Yes, for instance, my working group.
Und,
So indeed, this is a very contemporary topic, and it's one that has been done by very excellent research groups.
die Variante tatsächlich quantenchemisch
There's also the variant of quantum chemically simulating
man kann Simulationen
these materials on very big cluster
der Materialien
PCs.
berechnen und dann abschätzen zu können, okay,
to calculate the band gaps of these materials and determine whether they actually exhibit the properties that we're looking for. But actually, I don't know what the state of the art in this respect is.
muss man auch
But in order to do this
Strom und Energie und
precisely, we have to invest a lot of calculation power and energy. And it could still be that theory doesn't really match reality in this respect, or that the material works and has the property that we desire, but then degrades and doesn't exhibit the lifetime that we wish for.
nach der Nadel im Heuhaufen.
So it's really the literal search for the needle in the haystack.
Ja, wir haben jetzt über die Umwandlung direkt in Strom gesprochen, über die direkten Solarzellen.
Okay, we talked about directly
Aufspalten von Wasser. Gibt
direct electrolysis and changing the
beziehungsweise wir haben Fotos
electricity into water electrolysis.
die dann verbrennen, wo wir Energie haben wollten.
Mengen und Massen. Also da könnte ich wahrscheinlich den ganzen Tag drüber reden oder das ganze Camp lang oder sowas. Also
So I could talk about this for the whole camp, but are there any alternative processes to actually perform this?
Energie, also
Yes, for instance, bioenergy.
quasi Mais
So for instance,
Pflanzen züchten, um die dann eben in Biodiesel
for instance, corn crops and changing them into bioethanol in bioreactors,
läuft ja auch schon etliche Jahre.
which is also the refueling station discussion. This is actually being done, but I don't have the total efficiency in mind. I think, however, that it's not very big, just a few percent.
In Konkurrenz mit unserer eigenen Nahrungs.
And also, of course, we then compete against our own nutrition generation.
Thema habe ich absichtlich ausgeklammert.
I omitted this topic on purpose.
Pumpspeicherkraftwerke,
For instance,
mechanische Energie zum Speichern zu nehmen. Meines Wissens
Meint ihr jetzt schon Nutzen von
for instance, hydroelectric storages. This I omitted on purpose because it's another very big topic.
Ich hatte das verstanden als Ersatz für die Elektrolyse hinterher. Was auch gemacht wird, ist die Sonnenenergie, die
But what, for instance, is also done is to directly
Wasserleitungen zu fokussieren und damit
translate solar energy onto water just to evaporate water and then drive turbines with it, which is, for instance, done in Spain or in the Sahara Desert.
fällt mir jetzt gerade spontan nichts ein.
But otherwise, I don't have any spontaneous idea about other coupled processes.
Ein paar Fragen gehen noch.
So we have room for a couple more questions.
Okay, sie geht. Da? Gut, dann sind alle gut durchgekocht.
Okay, so everyone is heated up, and let's thank our speaker again.
You have listened to the talks